solidification processes can be divided into three categories, subclasses: metal casting, glass working, and processing of polymers and polymer composites and so on. Okay. So glass working, making of glass, and glass means hundreds of different kinds of glass. That is not our topic. And processing of polymers and polymer composites is not our topic. But casting of metals is this chapter, casting of metals, right? So casting of metals, as we just discussed a little while earlier, is expendable mold and permanent mold. All those casting methods where the mold can be broken, where the mold is used only once, are expendable mold. And all those casting methods where the mold can be used again and again, it is permanent, it is not broken, is permanent mold. We will study both of these kinds. And in expendable mold, the most popular in the world is sand casting. And then there are other casting processes which are expendable mold, right? Of course, we can give more details of this, that we can list all the expendable mold castings here, and we can list all the permanent mold castings here. But as just for a beginning introduction, solidification processes, one of the major is casting of metals. Casting of metals is expendable mold or permanent mold. And the most famous one in the world, called sand casting, is expendable mold, because the sand mold is broken every time we do the casting. Now the next few slides, solidification of metals. This is the topic in the book. The topic is solidification of metals. Now this is material science again, right? Because phase composition, phase calculations, calculations based on Lever rule, right? The phase diagram, solidification of metals, if you remember from material science, is phase diagrams. And phase diagrams for isomorphous alloys, binary isomorphous alloys, eutectic alloys, iron carbon diagram, all those you have done in a lot of detail in the material science course. So this I am leaving as a self-study. Okay, this I am leaving as a self-study. Remember, if I say this topic is not covered, then it is not covered. When I say it is a self-study, it means from solidification of metals, from iron carbon diagram, from other things, I can ask questions, either small MCQs and so on, or even small numericals. So please, from your material science, do a quick reading, and do a quick practice of the numericals that you did earlier. So this is the slide of temperature and density for castings. This is a slide for two-phased alloys, binary alloys. This is a casting for self-study phase diagram for nickel copper alloy. You have done that in the previous course. Phase diagram of iron carbide steel. You have done that in detail earlier, right? So that is why I have written in all of these self-study. This is given in this book also. So you can go through these slides for a quick review. You can go into the book of this section and you can quickly read it, or you can go back to your material science course. There was one chapter on phase diagrams and another chapter on alloys. So phase diagram was the general chapter about this, and in alloys we did only the iron carbide diagram, which is again phase diagrams. So you have done all of this earlier, but please, I can ask any question about phase diagrams and iron carbide diagram and so on. Okay, so do give it a quick self-study in terms of the theory also and the numerical part also. The next section is cast structures. Cast structures, that after casting, what is the crystal structure and so on. So this is not included, right? This 5.3 in the Kalpakjian book is not included. Okay. Therefore, now we come to 5.4, fluid flow and heat transfer. Now this is a strange topic, right? This is like your fluid mechanics course and your heat transfer course and so on. So one very good thing. Many times I have this feeling that when you are doing math courses, calculus 1, calculus 2, linear algebra, differential equations, a lot of you feel that this is not required by engineers. Similarly, when you are doing basic courses on solid mechanics, fluid mechanics, heat transfer, thermodynamics, I don't know if you feel that they are really required by engineers or not. I keep on telling all my students in all of my courses that you see, engineers will have a variety of jobs. Civil engineers are there. Civil engineers are there. They can design bridges and roads. They can design normal houses and buildings. They can design huge workshops. They can design an airport structure. So, in what type of job a civil engineer will end, we don't know. Therefore, we prepare you for all types of jobs. Mechanical engineers are even hugely versatile. You can go to any industry in the world, any factory, any industry, mechanical engineers are required. So, you may go into design, you may go into manufacturing, you may go into quality control, and in the type of industry, you can go to basic metals, aluminum alloys, how are they made, steels and iron alloys, how are they made. There are industries in Oman, mashallah. There is Valley Steel in Sohar, there is Sohar Aluminum, right, and so on. So there are metal industries. Then there are rolling mills and re-rolling mills, and there is Muscat Steel here in Russell. These are metals. Then there are polymer industries. There is Sohar Polypropylene and other polymer companies. Then there is PDO and Shell and so on, petroleum development and petroleum extraction. So you see, you can end up as a mechanical engineer in any type of job. So sometimes you will need fluid mechanics a lot, sometimes you would need heat transfer a lot, and so on. So therefore, at this stage, sometimes you feel that we are doing so many courses, we don't know where it will be used. Okay. Here what I wanted to say was that you see, we will apply very small amount of fluid mechanics and heat transfer here, but to what? To metal casting. This is the chapter on metal casting. So this is one major proof that the different subjects that you study are definitely applicable in different branches of engineering. It is only our luck whether we end up in this branch of engineering or that branch of engineering and so on. And you end up as someone like me, right? I did my bachelor's in mechanical engineering. I worked in the industry for several years. I did my master's in mechanical engineering. I worked for a few years in the industry. Then I did my PhD. Then I came back to the university. I thought that, you see, I will be more useful in transferring this knowledge. But in the university, say, I mean, I have been in different universities in the world, but when I've been in Oman for more than 15 years, I have continuously worked with the industry, with PDO, with Shell, with Baker Hughes, with rubber companies, with polymer companies, with steel companies, with aluminum alloys companies, and so on. So you work with so many different types of industries if you are in research and if you want to solve problems for them, that it is not that, you see, I know only solid mechanics or I know only manufacturing or everything is required. So either I become good at everything or I make a team in which some are very good in terms of fluids, some are very good in solid mechanics and so on. So with this, you see, 5 minutes of extra time where I was just trying to motivate you again that every course that we do is definitely required in some real practical field of engineering, but maybe we end up doing a job in that area or maybe we do not. So now this is your first major introduction to casting. What we have here is a cutaway. This is sort of a schematic diagram. A schematic diagram means that the dimensions and the materials and so on may not be exact, but it gives you the complete picture of what is happening. So if there is a sand mold, and vertically we cut it into half, we have sectioned it. Remember, in your engineering drawing, there was a chapter on sectional views. So we have a sand mold, and vertically we have sectioned it into two parts. So now this is what we see. This is a sand mold. From the top, we are seeing the outer side. From the right, we are seeing the outer side. But in the front, we are seeing inside the mold. So this is a standard sand mold. Okay. If you see now, this portion, this outer portion, may be a metal, maybe a wooden piece, this side, that side. So this is a box. This is a box inside which the whole mold is there. This is called a flask. In normal English, where do you know of this word? Yes, a vacuum flask, a thermos, right? Where you keep your tea and coffee. It can remain hot for some. It is also called a flask. So actually a flask means any container inside which there will be some material which you want to keep at a certain temperature and so on. You don't want to lose the temperature you can keep a cool drink inside and it will remain cold. You can keep a warm drink or hot drink inside and so on. So this outer portion which is here and which is on the other side and which is all around is called the flask. So right, so this is like the outer box inside which the whole sand mold is there. Now all this material is sand. All this material is sand, right? Sand we are showing here, sand we are showing here. So all this material is sand. We will talk later that there is a special type of sand which is used for sand molding. A special type of sand. The size of the sand particles should be in a certain range, and not every type of sand will be good for a sand mold, and we will have to mix certain liquids, certain binders, so that we can pack the sand more easily. So that is the sand, right? If you see here, there is a line from here till here, line, right? Above it is the upper half, below it is the lower half. So this line sort of divides the sand mold into an upper half and a lower half. So this is called a parting line. It divides it into two parts, right? To part means to separate. So parting line. So this line is there. Of course, this line is a surface. Right now you are seeing it as a line, but this goes all the way through the thickness, through the width. So this is actually a surface, right? So there is a parting surface. Above it is the upper part of the mold. Below it is the lower part of the mold. That upper part of the mold is called cope, C-O-P-E. All this is the cope part of the sand mold. And all this lower part is the drag part. This is just names. So we will have to remember these names. That the upper half of the sand mold is called the cope, and the lower half, the bottom part of the sand mold is called the drag. Okay. So there is a parting line or a parting surface. Above the parting surface we have the cope, and below the parting surface we have the drag. Remember, this is a cut away sectioned view. Otherwise the whole mold, the whole box is there. So for the whole mold, the whole box, the upper half is the cope, the lower half is the drag. Then we cut a conical path from one side. A conical path, if you see, this is larger here and a smaller here. So it is like a cone ice cream, right? So we cut a conical path so that we can pour the metal into the sand mold from here, right? We can pour this. So this top part is called the pouring basin or the cup. This top part is called the pouring basin or the cup, and this whole thing is called the sprue. This whole conical part is called the sprue, and the top of the sprue is the pouring basin or the pouring cup, where we pour the molten metal, the hot metal, into the sand mold.